Hello and welcome back to me answering questions from Robin Hartshorne's Algebraic Geometry. Today I will be answering question 1.10 of section 1. This is split into 5 parts, each of which will be answered here. The first part asks us to show that the dimension of any subset of a topological space is less than the dimension of the space as a whole. So, let me just make sure that I have the correct color. Yes. So, first of all, endow Y with the subspace topology. Let C be irreducible in Y. Be closed and irreducible, so closed and irreducible in Y. Now, that means that C is of the form Y intersect F. So C equals Y intersect F for F closed. Now we want to show that the closure of C in X is, fly, is irreducible. Fly is harassing me. Now, if Y was closed, then that would be easy. We would just say C is closed in X and therefore it's fine. However, that's not the case. So, suppose C was reducible. Then there exist A, B, proper closed subsets of the closure such that A union B proper closed subsets equals the closure. Now let's intersect with Y. Y intersect A union B equals Y intersect A union Y intersect B equals Y intersect this, which as C bar contains C, and it is, I'm so sorry if you can hear that fly. It really likes my face. Equals C. As in, if C equals Y intersect F for F closed, then C C bar is a subset of F, which means that C bar union Y is a subset of C bar of F union if oh my god. C bar intersect Y is a subset of F intersect Y. Which, to be honest, I can do this. C union Y, C intersect Y is C bar intersect Y is a subset of F intersect Y equals C. And therefore, and this is equal to C, therefore these two are equal. Well, therefore they're all equal, but these two are equal. So C bar intersect Y is equal to C. Yeah. Or Y intersect C bar is equal to C. Either works. But then we would have Aha. As C is irreducible, either one of these has to equal C. Uh, Either A equals C or B equals C. Now, if A equals C or B equals C, or A intersect Y equals C and or B intersect Y equals C, either A intersect Y equals C or B intersect Y equals C, therefore C is a subset of A or B closed. But as oh god, sorry, I lost my pen for a second. As C bar is minimal, this implies either A is a subset and not equal to C, C bar, sorry, which is itself a subset of A, which is a contradiction. And the only thing that we've supposed is that C bar is reducible. Therefore, oh my god, I'm so sorry. Therefore, C bar is irreducible. Now, we need to prove the other direction, I believe. Unless... I'm just reading my notes, I'm so sorry. Aha, this is just the next thing that we need to prove. Now we want to prove that if we have B, which is a subset of new B, so I should not be using B. If we have D is a subset and not equal to C, uh, we want to show that the closure of D is a subset not equal to the closure of C. That is what we want to show. So, we assume D is a proper subset of C, and both are closed or closed closed in Y. What on earth is this fly doing? It seems to be trying to make as much noise as possible, as close to my face as possible. No. Either the D bar is a subset of C bar because C contains D, and C is a closed subset. Sorry, C contains D. Oh god, and C bar is a closed subset containing D. Therefore, D bar is a subset of C bar, and the overbar for now means closure in X. So D bar is a subset of C bar. So either d bar equals c bar or d bar does not equal c bar. Now, what can that tell us? Well, we want to show that the latter is the case. So if d bar equals c bar, then y intersect d bar equals y intersect c bar. But this we have discussed and is equal to d bar, is equal to d, sorry, and this we have discussed is equal to c. This would violate d being a proper, this would violate the properness of d, therefore, which is a contradiction. So d bar is a proper subset of c bar. Now, what we want to see, let uh, y naught be a proper closed subset of y1 be a proper closed subset of dot 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 be, oh no, what? Oh, thank God. Be a chain of distinct, irreducible, closed subsets in Y. We have essentially shown all that we want to show. Then y naught the closure dot 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 y1 closure is a chain of distinct irreducible closed subsets in X, which is of the same length. Now, as the dimension of Y is the supremum of all chains of this form, and the dimension of X is the supremum of all chains of this form, uh, well, the longest chain in Y cannot be longer than the longest chain in X, because for any chain in Y you can cook up a chain in X, which is, well, of equal length. So therefore, I used lowercase letters, not uppercase letters. Therefore, the dimension of Y is less than or equal to the dimension of X. Now, that is what we wanted to show. So, let us move on to this next question. If X is a topological space covered by with an open cover, then the dimension of X is the supremum of the dimension of this open cover. Is the supremum of the set of dimensions of this open cover. Now, what we want to get, let X be a topological space with this cover. I will just write I here, or I in I. Be a topological call space with an open cover. Now, let us have a a chain of distinct irreducible closed subsets. So let y0 be a proper closed subset of y1, proper closed subset of dot dot dot. Be a chain of distinct irreducible. You know what? I will call it be an admissible chain. And an admissible chain is a chain of distinct irreducible closed subsets. Be an admissible chain. Or diam? I'm sorry. I will rewrite that. Chain. Now, as the UIs cover our cover X, we can find some index such that an element of y0 is an element of x0, of our open set. So since UI covers X, fix some element of y0. So I'm going to call it Z so that I'm not tripping over about, oh, is this a capital or a lowercase y? Fix Z and y0. I think I should write, well, for any Z and y0 there is an open set, but fix Z in y0 for any, yeah, sorry, I'm confusing myself. Thankfully, this is the only real difficult part. Well, it's not the only long part left. C and E give example questions. So fix Z and y0. There exists an index k in I such that Z is an element of UK, which therefore means that UK intersect all of our yi's are going to be non-empty. So hence intersect yi intersect uj UK is non-empty for all I, and yi intersect UK is a closed subset with respect to the subspace topology on UK, and an open subset with respect to the topology on yi. No, right. Is a closed subset in UK and an open subset in yi. Furthermore, yi intersect UK Okay, the closure it is dense. It is dense in yi. It is irreducible and dense in yi. Now, not only that, but any pair of closed subsets within yi is closed within X, and therefore you can intersect with UK those closed subsets, and those would be closed subsets which would union to it. Therefore, it's irreducible in UK as well. Now, let hmm. I will not write that. I've just explained it. So, if yi or yj intersect UK equals yj plus 1 intersect UK, then yi equals yj intersect UK, the closure in X, which is, well, yi is a closed set, and this is dense within yi, equals, again, yj plus 1 intersect UK, the closure of that, which is equal to yj plus 1. Now, not only that, that contradicts our construction of our chain, our admissible chain Y. Therefore, this is impossible, and so, therefore, Y naught intersect UK is a distinct irreducible closed subset of UK. Y1 intersect UK is a admissible chain in UK. And so the dimension of X is less than or equal to the dimension of UK, because for any admissible chain in X, we can construct an admissible chain in UK, but as UK is a subset of X, the opposite equality holds. Therefore, dim X equals dim UK, which again would equals the supremum over I of dim UI. Thus we are done with 1.10b. Now we move on to 1.10c. Give an example of a topological space X and a dense open subset which has dimension less than. Now, I I don't know if this counts, but I will. Well, I know it works. I just think it's a bit cheesy. Cheesy? Cheap. Hmm. Anyway, where is my pen? There is my pen. Let x equals 1, 2 have not open subsets. Well, open the following topology on it. Open, closed. For both of them, the empty set must be there. So now the closed sets are of the form 2, 1, 2. The open sets are of the form 1, 1, 2. Now, the smallest closed set containing 1 is 1, 2. Therefore, 1 is dense in X. Now, the dimension of I aha, I just need to check something. Okay, hello again. I should never have doubted myself. 1 contains no irreducible closed subsets because the empty set is not irreducible. Therefore, the dimension of 1 equals 0. Now, the dimension of 1, 2, well, is greater than or equal to the length of the following. Aha, minus 1 is equal to 1, not greater than or equal to. It is equal to 1 because there's, well, the only other chain is the chain of length 1, which is simply 0. If the largest chain is of dimension 0, if the largest chain is empty, is that not dimension minus 1? Well, it doesn't matter anyway because either or it's less than 1. Is less than 1. Let's just say it's less than 1. Q equals 1 is dense in 1, 2, but dim U is less than dim X. I'm not sure if you can have. Either or. Let's move on to 1.10d. If Y is a closed subset of an irreducible topological space and the dimensions are equal, then show Y equals X. We will do this contrapositively. Therefore, let Y be a proper closed subset of X. That O is ridiculous. The proper closed closed. What we want to show is that the dimension is less than the dimension of x. Well, any chain of irreducible closed subsets in Y lifts to a, well, any chain, any admissible chain in Y, I will again use this, any admissible chain in Y induces an admissible chain, not Dane, chain in X of the same length. Furthermore, the closure of any closed subset of Y is contained in Y, obviously, because the closure is defined to be the minimal closed subset containing. Therefore, Y contains that, obviously. Now we just need to show, well, that's the closure of any closed subset of Y is that set because it itself is closed because it's the intersection of two closed subsets. But what I wrote is technically true as Y is a proper subset of X. This chain, this induced chain, does not include X. Therefore, as X is irreducible, we can add it. Therefore, to any induced chain, we can add X, and the dimension of Y is the dimension of X minus 1. We can add X. The dimension of Y is less than or equal to the dimension of X minus 1. Therefore, the dimension of Y is less than the dimension of X, which implies that the dimension of Y is not equal to the dimension of X. Hence, by contrapositivity, we have shown this. Hence, if the dimension of Y equals the dimension of X, Y equals X. And now, finally, we are on to the last part, which asks us to give an example of a Noetherian topological space of infinite dimension. Now, I think the fly has... So my laptop is resting on some cardboard boxes, and I think the fly from earlier has gotten inside of those cardboard boxes somehow. It keeps flying against it, and very annoying. But I have constructed this example, let x be the natural numbers with closed subsets of the form empty, obviously, then, and obviously n, then 0, I guess n naught if you're wanting to force 0 to be there, 0, 1, 0, 1, 2, etc., etc., 0, 1, 2, 3, 4, dot, 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 n, for all n. Now, well, we have a admissible chain immediately, although we must show that each of these closed subsets is irreducible, but they essentially we want to consider firstly x is Noetherian. There is a principle that if you're counting downwards, then you will eventually hit the end of the natural numbers. I've completely forgotten what it's called. I think it's the well-ordering principle, but don't quote me on that. As each chain of descending closed sub subsets stay my goodness stabilizes. I think it's with as every ounce of my being wants to write it with an S, and I think that's just me being overly, I'm not sure, because I know that quantize, for instance, has a different spelling for Americans and British, and typically between the two, Americans try and make the orthography shallower, so yeah. Consider, sorry, consider 0, 1, dot, 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 up to R. Well, any proper closed subset does not contain R, therefore R is irreducible. Therefore, well, anything from here onwards. Therefore, 0, 0, 1, 0, 1, 2, dot, dot, dot. I think that well, up to 0, 1, dot, 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 m is an is an admissible chain in X. Of length m. Well, really of length m plus 1, but we're 0 indexing, so of length m for any m natural number. Hence, the dimension of X is the supremum of the natural numbers, which is infinity. Therefore, we have shown, and not only have we shown, but this is the last section, or the last part to this question. Therefore, thanks for watching. Goodbye. Don't really know what else to draw. I don't know what I was thinking. Anyway, goodbye.